slide, 1 hour board, but then too many things. So yeah, I'll do our slides as much as we can see. So probably 2 hour slides. It's 150 pages. Enough to cover.
Okay, everybody brace themselves.
Yeah. Okay. Okay. Good morning, everyone. Let's. We have viewing for this first of 2 talks, and if it goes over, who knows how many we will.
Yeah. Thanks. Thanks, Avi. Thank you all for coming. So today I will be talking about the complexity of isomorphism problems for several algebraic structures, including tensors, groups, polynomials, and algebras. So yeah, it's something I have been doing in the past, I don't know, 7 years or so, and it's a lot of several papers with many joint collaborators, actually a bit more. So I apologize if I don't list their names. I will mention them for sure during the course of the talk. So yeah, let's get started. So isomorphism problems, right? Many of you probably are very familiar with already. That is, if you are given 2 combinatorial or algebraic structures, you want to know whether they are essentially the same. And the most famous example is, of course, graph iso. That is, given 2 graphs, you want to know whether they are the same after relabeling the vertices. And you probably know this pretty well, but just to refresh your mind, suppose you have 2 graphs. One is 5 cycles, they are very star, they look different, but if you relabel the vertices, you will see that these 2 graphs are essentially the same. By mapping the vertices, you can preserve and respect the edge relations. So it's one of the, it has a pretty distinguished history in theoretical computer science. It's one of the earliest problems considered in the framework of P and NP. In the paper proposed the NP complete notion by Cook and Levin, Cook mentioned that he was not able to prove that graph iso is NP complete. We now know much better, right, why he could not do so. It's not his fault. And we also have Levin, who actually suggested graph iso is one of the motivations to define NP completeness. Then it's motivated a lot of great things. For example, permutation group equivalence by Babai and Lux. And also they are it serves as classical examples for interactive protocols like water fixer, Schroning, and also zero knowledge for graph iso and graph non-iso, like Goldreich, Micali, and Widerson. So yeah, that's graph iso. Then there's another even more,
I'm not mentioning Babai's algorithm.
Later,
Right?
I'll do that later, yes. Yeah, then there's also Babai's force of polynomial breakthrough for graph iso, of course, yes. I'll mention that later for sure. There's another very classical example, matrix equivalence. It's probably, too foundational. People don't really recognize it. That is, suppose you are given 2 matrices, A and B. You want to know whether these 2 matrices, A and B, are the same up to invertible matrices, left multiplying on the left and right multiplying on the right. So just, just to give you some examples, suppose you would have A and B, and you want to know whether there exists L and R, such that multiplying L on the left and R on the right, you transform B to A.
Do you think about integer matrices or?
These are integer matrices, so you can consider over any field, of course. Yeah. So yeah, so far these are integer matrices. In this example, it's integer, but over any field, of course, we know that A and B, the 2 matrices, are equivalent if and only if they have the same rank. Right? That's the Gaussian integration. So of course, there are 2 related notions, namely matrix similarity, where R is L inverse, A and B are square matrices, and matrix congruence, right? R is L transpose. So there are, of course, also important topics in linear algebra. So on the other hand, today we'll be mostly talking about tensors or multi-way arrays. So we are essentially generalizing from matrices, which is a 2-way array. And we should usually, in this talk, sometimes I just write, this is a square of numbers, right? So let me just write a square. It's not a square in the geometric sense, it's a square of numbers. So next step, of course, will be 3-way arrays, right? So I write this cube, but it's not a solid cube or something, but it's a cube of numbers. For example, this is like a 2 by 2 by 2 cube. You have the first slice, which is a 2 by 2 matrix. The second slice on the back is a 2 by 2 matrix. So sometimes we don't want to draw a cube. Maybe we'll just say that we have a matrix tuple, right? By listing the slices, we have a matrix tuple. So a matrix is a two-way array, and the matrix equivalence is defined by L and R invertible matrices, multiplying on the left, multiplying on the right. And the L, of course, is doing linear combinations on the rows, and R is doing linear combinations on the columns. So for three-way arrays, because now it's a cube, you can multiply on in three directions, right? So you have three invertible matrices, L, R, and T, doing transformations on the three directions, where L, is doing linear combinations of the horizontal slices, R, the vertical slices, and T, the internal of the slices, the third direction. So of course, then tensor iso is defined. We are given two cubes of numbers. We want to know whether there exist invertible matrices, L, R, T, such that when L multiplying on the left, R multiplying on the right, and T multiplying on the third direction, whether you can transform this one cube of numbers to the other cube of numbers. If you want to write it on the paper, you don't want to draw it, you probably want to say that, okay, I have two matrix tuples, and we want to know whether it exists invertible matrices L, R, T, such that L is multiplying on the left, R is multiplying on the right, and T is doing linear combinations of these slices. So that is tensor iso. Intuitively, I guess it's pretty straightforward. And of course, the question is, what mathematical content are we going to put into this problem?
Can you say something about the directions? Why is T on the left?
Yes, when you slice this cube, according to the third direction, then you get a tuple of matrices, right? And then L is essentially multiplying all these matrices on the left. R is multiplying all these matrices on the right. And then T is doing linear combinations of these BIs. So that's what the three direction action, if you write it in the matrix tuple form.
Is there any reason why you singled out one of the directions to be the third direction?
You will say that's very good. Yeah, so this is just for convenience. So we fix one direction so that we can write it on the paper, right? So, yeah.
Just write it as a three linear form, then it would be obvious.
The trilinear form, we will go to that, of course. Yeah, of course. Yeah, thanks. Yeah. So far, it's mostly, just like intuitive introductory. So, yes, so in the paper with Josh, we defined the so-called tensor isomorphism complexity class. It consists of problems that are polynomial-time reducible to the tensor isomorphism problem. So this is in analogy with the so-called graph isomorphism complexity class, where people define a problem to be in the graph iso complexity class if it is polynomial-time reducible to graph iso. And so far, we have like 5 papers on the complexity side of this complexity class. From 1 to 5. And we are motivated mostly by complexity considerations. And we are going to say that it will lead to very unexpected actions. So that's kind of like the prologue. Hopefully we know the problem. And now I'm going to give you, some of the main messages we found in this long study. So the first is that tensor iso captures isomorphism problem for many algebraic structures, like polynomials, algebras, associative or Lie algebras, as well as groups. So then that's the first message, showing that many problems are so-called tensor isomorphism complete. And the second message is that we have been mostly talking about invertible matrices or general linear group. Then you can transform to other group types, and instead of considering over in a field, or you can consider over rings. Then it will lead to connection to quantum information, geometry, and number theory. And then, so the third step, we will show some technical aspects of our work so that we get to know some of the things we do in the second and fourth paper. And finally, explain to you the current status of the algorithms, and if we can talk about cryptography.
Can I ask a question, since I've never seen these things before? Can you say something about what is and is not in the graph isomorphism complexity class?
The tensor ISO, we don't know, for example. Tensor,
Oh, you don't know, but what is known about the graph iso?
what known is about graph ISO.
For example, the counting the number of isomorphisms is equivalent to just testing isomorphism.
Yes,
That's
there are
what
For graphs.
for graphs, and
Right.
that's not trivial. It's not true about, or it's not expected to be true about NP-complete problem.
yes,
The counting version is the same as.
and it's in NP intersect co-AM. I will mention to you actually about this now. So it's unlikely to be NP complete unless the polynomial hierarchy collapses.
I'm just, okay, I thought there was an algorithm by Babai for this.
Yeah,
That's
but
possible.
it's not polynomial anyway, but
It's not
it's not poly, into the log and cube.
Okay, but it's not exponential either.
No.
It's something in
yeah.
between. We should think about it as something between really hard problems and.
Think of it as easy.
So like factoring
But
polynomials.
nevertheless, I mean, before it was known, there were several problems that were shown equivalent. And this counting version is perhaps the most.
So,
But how does it compare to factoring prime numbers?
But that we know it's much easier so far.
Graph isomorphism is easy.
There's no formal connection, I know.
yes, I probably should have drawn a graph saying that, okay, so if you look at the map of NP problems, NP complete are the most difficult, right? P is the easiest. There is some notion called NP intermediate. People think that there should exist, assuming P is not equal to NP, there should exist so-called NP intermediate, which is not in P, no NP complete. So graph ISO is still one of the candidates because we only know coarse polynomial-time algorithm, but it's quite close to P in a sense. On the other hand, for tensor ISO, you will see kind of for the algorithm, it's also NP intermediate over finite fields. It should be a candidate for NP intermediate, but it's much harder. It's more closer to the NP side. So
What about 3? I mean, if you use dimension 3 just for the introduction, or just
yeah, we will talk about dimension D and AD in general. Yes.
these are the same classes, or
Yes, they will reduce to 3. Yes. This like 3 set is NP hard and NP complete. Yeah, it's all in the next slides. Okay, so the first message is that tensor ISO should capture isomorphism problems for many algebraic structures. So yeah, just some basic facts to answer some of the Raymond's question. So tensor ISO appears first, it arises naturally in some context. It appears in coding theory as so-called matrix codes, and it appears in quantum information by the so-called SLOCC, stochastic local operation and classical communication, equivalence between quantum states. So these are things, appear naturally in different contexts. And the complexity of tensor ISO, it's really dependent on the underlying field. If we are talking about finite field, then it's in NP intersect co-AM, which is a randomized version of NP. So it's more like NP intersect co-NP, and it's unlikely to be NP complete unless, for example, hierarchy collapse.
This comes from AM protocol.
Yeah, AM protocol, yes. Or it's in SDK. So, but if it's over complex number field, we only know it's in the Arthur-Merdin class, which is a randomized version of NP, assuming generalized Riemann hypothesis. This is a quite general result by Corin on stellar sets. Basically, you can formulate solving tensor ISO as solving a system of polynomial equations. So assuming that the matrices you are looking for is variable matrices, and then write linear polynomial equations and so on. So a natural question here is something I find pretty interesting, is that tensor ISO over complex number is it in AM intersect co-AM. That is something we don't know. We kind of feel that this ISO type problem shouldn't be NP complete in general, for example. But we don't know how to show that it's in co-AM or tensor ISO over C. Okay, so then the relations between different types of isomorphism problems. So the following problems are shown to be polytime reducible to tensor ISO. The first is graph ISO, which we talked about. The second one is called code equivalence. That is, if you are given two linear codes, whether they are the same up to permuting the coordinates, or you are given two linear subspaces, whether they are the same up to permuting the coordinates. So that is code equivalence, studied in the coding theory since 1980s. And we essentially have this relation. Graph ISO reduced to code equivalence. That's known in around 1990, probably should have made a citation. And then code equivalence reduces to tensor ISO. So that's the basic relation between these three things.
Say something about these reductions?
Yeah. So the reduction from code equivalence to tensor ISO, basically there's a couple of reductions. There's one reduction in our work. We will talk about the technical aspect later, which you can somehow see, at least. Graph ISO reduces to code equivalence. Well, there's a one reduction in the 1990s, but there's also a direct reduction from graph ISO to tensor ISO. Essentially, you look at the graphical matrix spaces. There's a natural way to embed graphs into matrix spaces, and that's natural construction just works. So there are many ways to do this. So I can tell you about more details later. So. Okay, so now I'm going to introduce to you several other algebraic structures that there are isomorphism problems. The first one is called finite group isomorphism. Given two finite groups, you want to know whether they are isomorphic or not. And it has been studied in TCS, theoretical computer science, and computational group theory since the 1970s. And for two groups of order n, there exists a natural n to the log n time algorithm, first observed by Target.
When you are given the
multiplication table. Yeah, but in general also as well, because you are given the generator, then you can afford to list, right, all the group elements. This is essentially because a group of order n can be generated by log n many elements. Right? So you don't, at most, you can then you only need to see whether where this generating set matches to the other. So this is an observation, but very useful already. So for group ISO, there are two versions. Well, several versions, but we are only going to talk about two versions. The verbose version, where the multiplication table or the Cayley tables are given. So you have to write down the whole matrix, the whole multiplication table of the group, which is presumably pretty large. And then there's a succinct version, which is what people in computational group theory, for example, care most. That is, suppose your finite groups is embedded into matrix group over finite fields, and you only are given the generating set of the matrix. So then a lot of basic things here are already difficult, but group ISO, of course, is a natural problem here.
But if you're given a presentation, does that might make your life easier?
Well, then the problem is whether it's finite or not. It's already undecidable. Then we mostly just look at finite, right? So yeah, polynomial time algorithm known for some groups. Groups without polynomial subgroups and so on, but that's not very important. The important thing is that there's one group class that resisted decades of efforts. If you grab a computational group theorist or you grab Lassi Babai, he will tell you that, okay, this is kind of like the bottleneck. And this group is, from the group theoretical viewpoint, the structure is kind of simple because it's called P groups of class 2 and P groups of nilpotent class 2 and exponent P. Where P groups mean that group order is a P to the power of P. Nilpotent class 2 mean that the center contains the commutator subgroup, and the exponent P means for every group element, G to the P is identical. So you will see, the structure of this group is essentially determined by its commutator map. So it's kind of like a relatively, from group theory viewpoint, it's very simple, but from isomorphic technical viewpoint, it's quite tricky.
What does it mean that this specific group resisted? So what is a question that you ask about this group?
It's not a group, it's a class of group.
Yeah, so you give me two of them.
You want to know whether they are isomorphic or
And
not.
how do you give me the data?
Either of these two.
Even if you give me a multiplication table?
Yes, we didn't know how to beat this bound until very recently.
Okay,
Even
so
the
this you
whole-
always can do n to the log n.
Right.
And the question is whether you can do poly n.
Now we can only do n to the square root n log n. So yeah, this is very funny. So we will see that later. It's
And regarding the succinct, if you only give like a.
succinct version. Basically, from succinct version, you can basically go to the verbose version and list all the group elements, right? So there are a lot of basic things are even harder, like membership, group membership testing and so on. But there essentially the succinct version, basically you can reduce to the verbose version by listing all the group elements. And then we don't really know much better than this one. There we don't even know better than this n to the log n until you do the verbose version and do the n to the square root log n. So.
So the bottleneck is just for this set of groups with
Yes.
to distinguish two groups of this class.
Yes. Yeah.
And you know how many there are?
There's a very good question. So there exists. I'll write it here. Okay. So this is I just posted a paper yesterday about this thing. So the number of such groups is p to the 2/27 L cube plus theta L squared. This is known by Higman in the 1960s. And this 2/27 is an interesting exponent because this is the right exponent for all groups of order n. If you look at all groups of order n, it will be n to the 2/27. That's Haber's result, some log n stuff. Then what we did just recently is we can pin down this exact exponent coefficient of the quadratic term. So that's the number of groups. Okay, so yeah, group files are already very interesting. So then maybe I'll talk about another ISO problem called polynomial-time, polynomial ISO. So we are now given two maps from f to the n to f to the m. They are quadratic polynomial maps. And we want to know whether there exists a invertible matrix A, another invertible matrix B, such that A naturally acting here, B naturally acting here, such that these two polynomial systems are the same. We can also look at one example to get a feeling. Suppose n equal to 2 variables, m equal to 3 polynomials. And this A, changing the variables, doing linear combination of variables. For example, like this. B is doing linear combinations of the polynomials. And then you get such, after this, replace these variables like this, then do linear combinations of the polynomials like that, like B, then you get another system of quadratic polynomials. Now, of course, the question is, if you are just given these two systems of polynomials, you want to know whether there exists A and B, such that, after this transformation, you make the two systems of quadratic polynomials to be the same.
How is this different from matrix isomorphism? You can just view these as quadratic forms of the two matrices.
That's another very good thing, yes. You are basically seeing why these things are finally turn out to be all equivalent. Because they are, at the end of the day, all these structure will be recorded by 3 real arrays, but with different group actions. So this problem has been studied in cryptography since 1996. The paper by Patron introducing polynomial ISO. His hope was to making use of the Goldreich methodic regression, zero knowledge protocol, and Fiat-Shamir to create digital signatures, for example. But then graph ISO turns out to be too easy, and so he proposed, let's look at polynomial ISO. And when he proposed this in cryptography, due to practical and considerations, he also proposed several variations. For example, maybe you set B to be identity. This problem may already be very hard. And then there's a difference between homogeneous polynomials, inhomogeneous polynomials, or you change it from quadratic to cubic. There's a host of problems or variations you can make.
There's some attack of Shamir on this, no?
Yeah, there is, yes. So he proposed this, then it has been attacked, and and then the story there is that there seems no guidance as to which cases are easy and which cases are hard. In a sense, it's saying, kind of suggesting that we may be missing some complex theory for this type of problems. For example, if B is set to identity, actually there exists a polynomial time method. If you think about this, it's actually not quite obvious because A is acting quadratically, right? It's A and A transpose. So it's acting quadratically. You have a system, so it's really unclear why this should be in polynomial time, but it is over finite field. When I say that there's no complex theory, actually it's not quite true because Algebra and Saxena, after their primes in P paper, they were looking at these problems. They were able to show some very interesting polynomial time equivalence between, for example, cubic form isomorphism, as polynomial iso when you have homogeneous cubic polynomials, and algebra iso. So let's look at algebra iso. Algebra iso is that you are given a finite dimensional vector space U over a field F, and you are looking at bilinear maps F and G, which from U cross U to U. This is like the multiplication in the algebra sense. And of course, we want to know whether there exists invertible matrix A such that now A is just for acting on U, right? Acting on U here, acting on U here, and then acting on U here. So you want to know whether these two algebras, they are the same up to this transformation. And of course, if you impose commutativity, associativity, Jacobi identity, you get the algebra, associative algebra. So it has been studied by Grigoriev, Kaya Saxena, Agua Saxena, Groucho, several others. So summary is that we have seen isomorphism problems for tensors, groups, polynomials, and algebras. They are studied in different communities, usually kind of in long history, TCS, computational group theory, crypto. And needless to say, all these structures, each itself is like a own topic, right? Or algebra, polynomials, and so on. So then here comes the result, the first result. From an isomorphism testing viewpoint, these problems are polynomial time equivalent. So this is the first result. These problems are PI complete. Namely, when you're given succinct group iso with P groups of class 2 exponent P, polynomial isomorphism, even when you're just restricting to quadratic polysystems or cubic forms, and algebra, even when you restrict to consider associative all the algebras, the isomorphism problem for all these algebraic structures are polynomial time equivalent, subject to some technical restrictions, like when you talk about P group iso, it's over GFP, finite field of order P. Quadratic polynomial system iso, you're not working with field characteristic of not 2. You need to divide by 2 somewhere. Cubic form, you don't want to work with field of characteristic of 2 or 3. So there are like some technical restrictions, but I hope that the message is clear.
Is it important to understand what you mean here? What do you mean over, like P group iso is over GFP?
Yes, we will see that why it happens there because
that's what it means. But what do you mean that?
Oh yeah, when I talk about P group iso, I mean tensor iso over GFP. Then it's over finite field of order P. P group iso is equivalent to tensor iso over this field.
Oh, okay.
So yeah, here is our now picture. We used to have this, right? Graph iso reduces to port equivalent reduce tensor iso. And it's also known that the verbose version of group iso reduces to graph iso. And on the other hand, now the new thing is that for tensor iso, succinct P group iso, polynomial iso, and algebra cells, they are polynomial time. So this give you hopefully will give us a better understanding of the isomorphism of all these algebraic structures. So now, yes, some question you already asked. Recall that matrix equivalence is in P, right? Matrix is 2 tensor. And we will see that 3 tensor iso is much more difficult. Then the natural question will be, how about 4 tensor? Or even D tensor in general? Where 4 tensor, you basically mean that you have array with 4 indices. Then you want to know this array with 4 indices are up to the invertible matrices of 4 invertible matrices acting on the 4 indices. So this is the 4 tensor iso. You can generalize to D tensor iso. And the result is that for D larger than 3, D tensor iso polytime reduces to 3 tensor iso. This is basically like 2 set is in P matrix case. D set reduces to 3 set, which is in P complete.
But it's not complete for D equals 4 is not complete.
It's also complete. It's another. Yes. Okay, so so far we know quite a few things, but I think this is like in our first paper. We are happy about this, and at least we get a better understanding of the isomorphic testing of all these algebraic structures. Now we are going to some funny things like quantum information, geometry, and number theory.
Can we just go back with like about the matrix two tensor equivalences in P? So we did see that it encodes graph isomorphism,
No,
but right, so but maybe that's only if we allowed like permutation matrices.
Right, for matrix equivalence, we are talking about left and right multiplying invertible
By
matrices.
any invertible.
Yeah, but if it's just a permutation matrices, actually we will see some variation of the theme later.
Right, so are you also gonna consider tensor problems where you restrict the?
Yes, yes. Yeah, I think you are all predicting what I'm going to talk about, so. So yes, actually, I'm going to talk about it now.
Ah.
So we have been focusing on invertible matrices transforming the tensors, right? So LRT, they are invertible matrices, or they from general linear group. So how about we consider revarying the theme and considering LRT as unitary or orthogonal or symplectic matrices, where unitary, as you know, is S conjugate transpose identity, orthogonal S transpose identity, symplectic, or preserving some symplectic formats. So what about these things? It turns out that these problems are actually also studied in different contexts. If you are talking about orthogonal group over real number field, such tensors are called Cartesian tensors in data analysis. If you are talking about unitary over complex numbers, then it's basically a so-called local unitary equivalence of tripartite quantum states, because we are talking about three tensors now, so it's tripartite quantum states. So, these things problems do appear in different contexts. And now we just, make up a definition. We make a definition saying that we let CL be some group class, like symmetric group, just as you were suggesting. Symmetric group, general linear group, unitary, orthogonal, or symplectic. This some group type, then you can define tensor iso under CL, under such group action, you can define complexity class by restricting that the tensor iso is with respect to such group class. Then many results in the GL setting carry over to unitary, orthogonal, and symplectic. I just mentioned one result, that is, we can show that D tensor iso over unitary group action reduces to 3 tensor iso over unitary group action, which in quantum information will be interpreted as D-partite pure state local unitary equivalence reduces to tripartite pure state local unitary equivalence. And if you
the complexity increases with D. This is for D constant, I feel.
it does not, the reduction basically is that if you have a D part, each part is dimension n, then the parameter range is n to the D, right? Then the tripartite, you have 3 vector spaces, each will be like n to the D.
Okay.
So in total, it's n to the 3D is still polynomial in the
D for constant.
Yeah.
For satisfiability, even if D was n itself.
That's true. That's true. Yes. So if you want to be more physicsy, you can replace local unitary, which is still mathematical, with something called local operations and classical communications. This is some work by Bennett and collaborators showing that these two notions of quantum states equivalence, one is mathematical, the other is physicsy. They are equivalent. But this is not very important. Then we can consider also the relations between tensor iso with these different group actions. Tensor iso with under symmetric group action is actually equivalent to GI, graph iso. So they will be contained in our work. We only know that they will be contained in TIU, TIO, simply because symmetric group can be embedded as unitary and orthogonal groups, but we don't know about symplectic. Then TIO and orthogonal and TI symplectic, they are contained in TIGL, but we don't unitary, because unitary is not really preserving some form. There will be some underlying field.
And just
Actually
the
don't
containment,
understand.
sorry,
Yeah, maybe.
containment of the group.
Yeah, it needs more
imply
work. It needs more work. You're right, for sure. It needs more work, but intuitively.
Intuitively, it's actually, my intuition is completely opposite. like linear programming is in P, but if you insist on integer solution, integers are contained in arrays.
Right,
And
it's a different
becoming,
context.
hard. So,
Yeah. It's
It sounds obvious. You know.
some proof is needed, yes. Some proof is needed to show this. But intuitively, so you can embed symmetric permutations as, for example, so if you write a permutation as a permutation matrix, it's in the orthogonal group, then you can do something, you need to prove that.
So basically, you show that if you get an isomorphism with orthogonal unit.
Yeah, you need to get back to
and make it a permutation.
but,
Yeah.
I mean, even for 2TI, for tensor isomorphism with dimension 2.
That's a good point.
TL, it's in.
This is a very good point. This is just for 3 tensors. Yes, that's a very good point. So mainly, if you will consider 2TI, then things are different. Because there, permutation makes things harder. You're right. You're definitely right. And even for the code equivalence, for example, if you permute the coordinate, instead of permuting the coordinates, you do full linear transformation, then it's also easy, right? So yes, you're right. Yeah. There will be some funny thing going on, but here is about 3 tensor. Yeah. Thanks. Yeah, thanks. That's a very good point. Okay. Yes, and recently, Lisikov and Water, they can show that actually that TI unitary is contained in TI-GL. And it's come via some very different method, and it's a very interesting paper. I can talk about this later. But some previous open talk question was recently just resolved.
Can you remind us how you define unitary and orthogonal? I mean, unitary and orthogonal are the same thing, just in different fields.
This is a complex number. This is a real.
Oh, you are working on the complex. I see. I thought you meant this on any field. I see. You really mean the complex number.
More complex. Okay. So we have been seeing that we can vary the group types, and we have some interesting experience. So namely, if you change GL into unitary orthogonal symplectic, we have some interesting things. The next thing will be to vary the field.
Here you have the field, right? So then unitary and orthogonal is just the same over a different field.
For some fields, yes, yeah. But when we talk about unitary, usually it's about a quadratic extension of the underlying field. So you have proper unitary, you're right. Now over commutative rings, okay. So we change F to rings, such as integers or mod R integers, integer rings and so on. So yes, so now we are going to change from fields to rings. And we'll be mostly looking at just restricting us to commutative ring, because if it's non-commutative, tensor product is already hard to kind of define. And we'll be also mostly looking at the ring of integers and the ring of mod R integer rings. So here, what does GLNR mean? It consists of matrices with determinant being a unit, namely invertible element in R. So if it's Z, it's just +1 minus L. And then vector spaces will be generalized to R modules. And here now we have come to see some funny phenomenon. Modules can be free or not, right? So there can be free module, which is R to the N, like our good old vector space. Sometimes they are not, right? Like 0 and 2 here, there's no basis here, so it's not free. But yeah, regardless of all the difficulties, let's just define, right? We define R is a commutative ring. The free tensor iso over R. Well, we can define the general version, namely tensor iso over R for general modules. And we can define a free version, namely, if we just look at free R modules, tensor product free R modules, you have different versions. But it's still the same story. Yes. And so if we are working with modular rings, and here if we restrict R is a prime power, there's some motivation from testing P group of class 2. And we were talking about general exponent rather than just exponent P. So this is why this class is interesting. If R is a prime power, then something will arise from group iso. But it is over Z that we really need go into some deep waters. Somehow we first saw something from Calabi-Yang. Then we got bumped into something Bloom was about decidability results for arithmetic group actions. And from there, we also somehow bump into Bagwell's approach for Gaussian composition laws. As you know where deep water is, and I don't think I'm qualified to understand these things very well, but there are people in the physics building there. Otherwise, but regardless, I'll just try my best to tell you our experience. So Calabi-Yau threefolds, which are Calabi-Yau manifolds of complex dimension 3, of great interest in string theory, classification is a big problem. So that's what I know so far. You can probably justify by graph somewhere from physics building. At some point, we came across this paper, identifying equivalent Calabi-Yau topologies, a discrete challenge from math and physics for machine learning, which is the MIT theoretical physics report. And in that paper, we found this challenge. Given 2, 3 index symmetric tensors, which is associated with the so-called Calabi-Yau threefold geometries, that there exists the integer linear change of basis, which is SLNZ, just means determinant is 1 rather than plus minus 1. You want to know whether these two tensors are the same up to this change of basis applied to it. Then I learned some names. CIJK is called triple intersection numbers between divisors. They are natural numbers, is symmetric. IJK equals JKI. And then there's a classical theorem by Wu in the 1960s, which said that 2 Calabi-Yau threefolds are diffeomorphic if and only if they are triple intersection tensors, and a bit more regarding second chain class and hot numbers, which again, just names to me. Apologize for that. They are isomorphic under SLNZ. Yeah. So then this is their challenge. And then we saw that problem, and we know that this problem is something we have been looking at over the field setting. It's, you can say that this is somewhat different, right? It's somewhat different from the tensor iso, because tensor iso will have 3 matrices, 3 invertible matrices, left, right, third direction. Here is just 1. But this is something we can handle without with some difficulty. But we can show that the symmetric tensor iso is a free tensor over Z complete. So this problem from Calabi-Yau is free tensor iso over Z complete. So then that
you move from 3 different matrices to 1 matrix.
yes,
The
yeah.
same
And
one
you get
over.
the same.
Same one.
Because the tensor itself is symmetric.
This is symmetric, so it needs to the same one acting to preserve the symmetry of the indices 3. So of course, the next thing is that they are actually looking for algorithms to solve this problem. They were not aware of the thing I'm going to tell about. So they say that, okay, there is no algorithm, let's throw into machine learning and see how things go. That's kind of like a lot of things happening now.
How did it go?
Not very well. Yeah. So, but on the other hand, in general, right, we can ask what is the complexity of tensor iso over Z, right? Is it decidable to start with? Then we bump into this paper. I think it's some paper I was talking to some geometric group theorist in my University of Technology, Simonyi Elder. And he was saying that, okay, there's some algorithm in this paper, in this paper. And from this paper,
The title of the paper is some general algorithm.
yes. It's a very general title.
In China.
You were not aware of this, I think, there's some general algorithms.
Yeah, we start general.
So yeah, it's a very general title. And then this says, have this theorem. If you have GLNZ or GLN over any number field, then you have some rational representation. Essentially, we are looking at actions or natural actions. Definitely the action on the symmetric 3 tensor is rational. So then given 2 vectors in this space, then there exists an algorithm deciding whether, when some group element transform one vector to the other under this group action. So this is Bloom-Wassergau. It's very general. It's pretty general in a sense. It's any rational representation. It's so
This is just a decision procedure, finite, no analysis.
No complexity analysis. At least they didn't bother to do so, I guess. So tensor iso over GLNZ is decidable. Okay. Then the question is, what is the complexity? This is kind of open, right? We want to understand what is the complexity of Gromov-Gauss diagram. Unfortunately, you can imagine using Tarski's decidability result for reals. So the complexity bound won't be looking so good, but
Remind us of what that is.
Tarski.
Yeah.
Yeah. So this is saying that the elementary theory for the for real involving real numbers is decidable. It's something.
You get a polynomial inequalities in the real, and the question is solving.
Okay.
So Tarski is quantifier elimination technique. It's finite. It's decidable. It's one of the earliest decidability results. That's not.
Thanks. Okay, so that's decidable, which is good, but it's that algorithm probably be too difficult. So then we are saying, okay, what is the complexity of tensor S over GL2Z? Now you just have 2 by 2 by 2 tensor, 8 numbers. So by Gromov-Gauss is decidable. That of course we want to do better. So we found this paper by Bhagawa in 2004, where he proposed a new way of looking at Gauss composition. And it's probably the first step of the works, a series of important, significant works leading to his Fields Medal. And from this paper, we found this picture, 2 by 2 by 2 tensor. So yeah, we are happy. And let's see what he's looking at. He's talking about it. So then this theorem is not from that paper, it's from his ICM talk, survey paper. Basically, if you interpret this theorem, look into this theorem, it's saying that there is some correspondence between the set of non-degenerate is something need to be done for that. Between G orbits on the 3 tensor, 2 by 2 by 2 tensor, G is this one, SL2Z, SL2Z. And the set of isomorphism classes of pairs, S, where S is a quadratic ring, and this is a triple of oriented ideals. Basically, if you move from SL to GL, then you can forget about the orientation. That's it. The important thing about this theorem is that it's for us, of course, it's very significant, but for us, we see some correspondence between G orbits, which is group theoretic, and the ideal triples, which is number theoretic. So we go into that. Of course, this is mostly done by Josh and Kate. But we go into that, then we can show this thing, namely 2 by 2 by 2 tensor S over Z is actually poly-time equivalent to testing if our ideal is a principal in the number field order. So it's equivalence between problem, which is more geometric, more group theoretic, and problem, which this is a classical problem in algorithmic number theory. So which has been studied for a lot, and then by result of Hogren 2 by 2 by 2 tensor ISO, which solved this problem, then 2 by 2 by 2 tensor ISO over Z is in quantum polynomial time.
Oh.
Okay, so good. Yeah, so we have some better than decidability result, and quantum polynomial time is still polynomial time. Okay, so I want to summarize a little bit. We start with tensor ISO over GLNF, where we have TI complete problems, including group ISO, poly ISO, algebra ISO. And we also have D tensor ISO reduced to 3 tensor ISO. Then we change group from GL to some group class. We're symmetric, unitary, orthogonal, symplectic GL. Then we see application of quantum information and of course a question in their relations. And finally, we talk about GL and R, where R is a commutative ring. If we are looking at a modular ring where R is a prime power with atom testing of P group of class 2, we make progress on that. Then if R equal to Z, then we see all these big names coming into the picture.
Are we going to see the reduction from D dimension to 3 or not?
I can talk a little bit about that, but I didn't.
What do you plan? Just ask maybe, otherwise.
It's I can see actually from D tensor you can do something called path algebra. You can use some quiver to encode tensor relations. So you go from tensors to algebra. Then you go from algebra to three tensor because so that's like two-step.
Can I ask a question about the last result you showed? This is about Z2 times Z2 times Z2, 2 by 2 by 2 tensor isomorphic, right?
Yeah.
Do you believe that 2 by 2 by 2 is fundamentally easier than, let's say?
That's my belief. We'll put, for example, 3 by 3 by 3, I don't know. Maybe, if I'm definitely not very qualified to say that, but I was surveyed, there's 2 by 3 by 3. So I don't know about 3 by 3 by 3.
And on 2 by 2 by 2, you have some strange Abelian group sitting there that's a Gauss composition, Lord. I don't think that, well, I have no idea. I don't know. I don't know if there are such magic happening higher tensor.
Yeah, well, let's forget about number theory. Could it be that all of the complexity classes you've introduced are quantum polynomial time, or do you not believe this to be true?
I feel that over Z, for example, I feel that it would be decided even some better generic upper bound. I don't know, polynomial hierarchy, exponential space. I don't know. So. Okay, so maybe it's a good time to take a 5-minute break. Okay, so maybe we can get started. And I was thinking of doing some technical aspects first, but because we were talking about how hard these problems are, I just maybe showcase the aggregate data so that you get an idea of how these two problems compare. So this is like for tensor iso and graph iso. So what are the aggregate problems? So we'll be mostly looking at graphs with invertices and n by n by n tensors over Fq over finite field. So everything is finite at least to start with. So the brute force for graph, of course, I'm omitting a lot of lower order terms, but brute force will be n factorial, trying all the permutations. And for n by n tensor, it will be q to the n squared or q to the 3n squared, but it doesn't matter much. So this is a brute force, trying all the invertible matrices. So worst case algorithm, which is, I should have mentioned this a long time ago as demanded by Avi. The breakthrough is by Laszlo by 8 years ago, I think now. So that's n to the O log n squared. So on the exponent is 2 to the log n cube, right? So it's much better than general exponential, but not yet polynomial.
Do you have any gossip why in 8 years it's still not in the journal? I know it was submitted, but
we can talk about it later.
Okay. So yeah,
He's
we don't
recorded.
But I don't know in general. So okay. So for worst case, for n by n tensors over Fq, this can be done improving from n squared to n to the 1.5. If you remember for Avi, for example, before this algorithm, the graph iso is like 2 to the square root n. So this is a little bit like that. This is like you have a q to the n times n square root n. So it's a little bit like that before Baba's breakthrough. So the average case can be done in linear time. This is Baba cell code in the where the average case means that you are given an arbitrary graph and the other graph is random. So you want to know, with high probability, you start with a random graph, then you need to test the random graph with isomorphism with any arbitrary graph. So this is the average case setting where you can have arbitrary distribution for the random graph model.
But the study is
If you look at local neighborhoods.
local degree sequences. Yeah,
but
it's not interesting.
Okay.
but it's some work.
Yeah.
For average case, you can also ask for tensors. You have a random tensor. You have n cube entries. Each entry is randomly chosen from Fq. Then you want to test isomorphism of this random tensor with arbitrary tensor. It can be done in time q to the On.
Nothing better.
Nothing better. Even heuristic. For practical algorithms, for graph iso, there's implemented software since 1980s. McKay is probably the expert on this topic. The recent update, like around 10 years ago, I guess. Basically, they have an algorithm called naughty and trace, which is implemented, can solve like a million vertices easily, graph ISO. So they're the
You mean even the worst case median?
well, practical mean that for the graphs you meet, this heuristic algorithm, no worst case. It's basically, for example, worst case algorithm would use group theoretic and combinatorial. But for practical, it's mostly just combinatorial with the lemon, of course, many very intriguing heuristics, shortcuts, and so on. So there, the game there is to find some graph that is slow on such software. It's basically very fast for like all the graphs you meet in practice. So people there, they want to devise graphs that are hard for such software. On the other hand, for practical algorithm for tensor ISO, we also have some heuristic algorithm, which we can analyze the heuristic complexity should be something q to the 1/2 n. Okay, so it's it's here O. This O is probably hiding 4, 5, 6, which is not very useful in practice, because in practice you want something like here should be 15. So if O is hiding 5, then your n is 3, so it's not very useful.
But anyway, that's more a random graph or random tensor.
Random tensor, right?
That's not very interesting. Never show up.
Random tensor here is interesting because cryptography.
Yeah.
So yeah.
But you don't mention a non-deterministic complexity. So tensor isomorphism like graph isomorphism, it's in NP.
NP, yes.
And it intersects AM.
Yeah, I mentioned at the beginning.
Okay, yeah.
I mentioned at the beginning. So yeah, any questions? So
You believe that for even in the worst case, like e to the n polylog n is probably the right. It's just an analogy with Babai. The analogy with Babai would be e to the n polylog n, roughly speaking. If you had a Babai.
If my personal belief, I think it should be q to the on.
On.
Yes, I think worst case. My personal belief that it should be in q to the on, but even practical, we don't know how to do much better than q to the say 1/2 n. So basically, this, you can see from the contrast that graph ISO compared with tensor ISO, this is in general easy, right? Worst case before Babai seems thought to be hard, but now Babai algorithm comes out, it's not hard. Tensor ISO, then every aspect it seems to be hard. So
the average case is as simple as the graph.
Not quite, because here tensor is represented by n cube numbers. Each number is log cube bit, right?
No, I mean the algorithm. What do you test there?
Oh, the algorithm, how hard the algorithm looks like, right?
Yeah.
It's actually it's inspired by this algorithm. The idea here is that you have n matrices here, right? N by n matrices. You write your tensor as a matrix tuple. Then you have another n by n matrices. You want to know linear combination of these n matrices will be up to left and right to be the same as the other tuple. So there you basically want to guess. For example, the first matrix map to which matrix in the linear span. So but this linear span already q to the n, right? If you want to enumerate matrices in the linear span, it's already q to the n. The idea is that if you guess the first, 4 or 5 images, then you will have very severe restriction on the left and right. So it will be also q to the o. So this is how they are. So the algorithm is easy, but the analysis is harder than this one, I would say. This one is not so easy in the sense that you need to do something for that.
Actually, I don't understand this problem because you have some given tensor and then you're given another one that's a random one.
Yeah, usually you think of this setting. As you will see in cryptography, there are people basically care they are in the same orbit. So you are given a random tensor, then you do some random transformation of the tensor. So you produce another one in the same orbit. So you know actually they are isomorphic.
Okay.
I gave these two tensors to you, hide the transformation matrices as my secret. You want to find the transformation matrices. That's my secret key, right? If you are the attacker.
So that's the average case we're talking about?
Yeah, that would be easier to think, yes.
Okay.
Yeah. So random tensor, namely you random fix the orbit. Then do a random transformation, you find another element in the orbit. I give that to you, how to solve this case. Okay, so I think I definitely prepare a little bit more than I want to talk about, but so maybe we'll say a little bit more about this algorithm side and then see if we have some time for technical. Is that okay, or we want to go back to the the complexity theoretic stuff?
Whatever you think, you are the boss.
You really the boss, right?
You're the boss, yeah. Sorry.
That's for the rest of the semester.
Okay, so maybe I think what I'll do is that I'll go back to the complexity theoretic setting to at least give because I see a lot of things about equivalence between problems, right? So at least there you see why this, but I think many of you already see. It's essentially the three tensor or three-way arrays are underlying a lot of things. So I go to that, but maybe do not go over everything. I do not go over everything of the technical aspect. So I just maybe you go to the point where we see why these things should be equivalent. Then we'll jump to the crypto part maybe. Okay. So let's go back a little bit. That is, we want to show that the group iso with this strange group class, polynomial iso, algebra iso, we want to show that they are actually polynomial-time equivalent, right? So the first idea is to realize that the three-way arrays, a cube of numbers, they are underlying all these structures, but with different group actions. This is also the case for matrices, right? Matrices is an overloaded term for sure. Sometimes it's actually a bilinear form. Sometimes it's a linear map. So this is similar to that setting. Then our goal will be to relate different group actions by so-called two methods. The first method is Gelfand Panamerov method from linear algebra, where people are interested in classifying tame wild linear algebra problems. And the complex theoretic method, the gadgets where computer scientists would like. So group iso. Group iso, remember, we are looking at this group of class-wide exponent P, and P is odd. But the important thing is that from the group structure viewpoint, the structure of such a group is completely determined by the commutator map. Because of all these constraints, the commutator subgroup will be isomorphic. It's elementary ability, that P to M. The commutator.
Yeah, I mean, it's effectively, we should believe.
Yeah, the commutator quotient is also isomorphic to some elementary ability group. The commutator map will be skew symmetric and bilinear. So you have a commutator map, and basically
the commutator map sends two elements to their commutator.
Yes, yeah. Because it's class 2, so the commutator map makes sense, for this quotient, from quotient cross quotient to the subgroup. So then so-called Bayer's correspondence basically saying that such P groups are determined by the commutator map, categorically, if you want. So skew symmetric, so we come to this problem, right? Skew symmetric bilinear map isomorphism, where we have finite vector spaces U and V over finite field of order P. We have two symmetric bilinear maps, and we want to know whether it exists A and B, A acting on U, B acting on V, making these two symmetric bilinear maps to be the same. And of course, for such bilinear maps, we will represent it as a tensor, right, by fixing bases. And then the question of asking whether they are isomorphic or not becomes to find invertible matrix A acting on the left and acting on the right for one side, and B acting on the third dimension on the other. So this is a bilinear map isomorphism. And then algebra isomorphism will
wait, it's not obvious why the problem with the same matrix on the left and the right is easier or harder than the one with?
We are going to that.
We're going.
We are going to that, yeah. I think, yeah, you're just predicting what I'm about to say. But I just want to, to refresh your mind, algebra ISO, you also have these bilinear maps, right? And now it's the same matrix A acting, in this way. And if you have two, so there, of course, you first represent by such bilinear maps as a tensor. Then you have two such tensors. They are isomorphic in the algebra sense if there exists an invertible matrix A acting on the left here, acting on the right here, and A on the other side acting on the third direction. So this is an algebra ISO group action. Finally, let's go to cubic form equivalence, which appears in the Calabi-Yau setting. So cubic forms, they are, they are homogeneous degree 3 polynomials. And you want to know whether two cubic forms are the same up to linear transformations on the variables. And there are some, we assume field characteristic, assume something on the field characteristic. Do the natural thing you would expect when you go from quadratic forms to bilinear forms. You get a symmetric trilinear form. So there is some symmetry among the entries. So you get the symmetric trilinear form. Now to test whether two cubic forms are equivalent or not, it comes to test whether these two symmetric trilinear forms are the same or not. But now it's the A acting on left, right, and third direction on the same tensor. This will matter. To summarize a little bit, tensor ISO is this, right? You have two cubes of numbers, but three invertible matrices A, B, C acting on the different directions. Group ISO, you have these two cubes of number, but A acting on left and right, B acting on third direction. Algebra ISO, you have A here, here, but A on the other side, third direction. Cubic form ISO, we have the three things, right? But the same A acting on the three direction on the same F. In other words, three-way arrays with different group actions encode different algebra structures. And we want to relate the different group actions for the three-way arrays, right? As Avi suggested, let's look at what matrices will do, will give us some hint. So matrix, of course, you have matrix equivalence, where you have linear maps from U to V. And here you have two, because U and V are not identified, you are not the same, so you have A acting on the left, B inverse acting on the right. Then if you have matrix conjugacy or similarity, then you have the U from U to the same U, then you will have A and A inverse on the left and right. So now we ponder a little bit, okay, they are both considered to be easy problems, right? They are probably polynomial. Matrix conjugacy actually is trickier if you want to compute the normal form and so on, but they are both easy in a sense. So now let's compare. We want to compare these two group actions. So we assume that they are all square matrices. For convenience, let's consider over algebraic closed field. The matrix equivalence, if you look at its orbit structures, it's just determined by the ranks. So there are n+1 orbits. It's finite, right? On the other hand, matrix conjugacy, you have Jordan normal form. So at least you have infinitely many orbits, though it's considered to be classifiable. So from the orbit structure sense, matrix conjugacy is more complicated than equivalence. Now the question is, how do we compare the orbit structure? And this goes back to Gelf and Polynomials, where it's probably in the 1970s when people were thinking about, in Soviet Union, were thinking about comparing different classification problems in linear algebra. So they mentioned the following to compare group actions. Suppose you have G acting on S, group G acting on set S, another group H acting on T. And they certainly partition the underlying set to orbits. Then Gelf and Polynomials propose that the latter action contains the former action if you can find a map such that this map should preserve and respect orbits. Namely, S1 need to map to here, S2, for example, map to here, and S, I don't know, W, map to here. The bad case will be if you have two orbits from here.
The map is from S to T.
From S to T, yes.
And that's from the sets that are being asked.
That's right, I said the map from S to T. So the bad case will be, of course, if you have two orbits from S mapping to the same orbit on the T side, or if you have some orbit, some mapped to cross orbits here on the T side. So this is pretty natural, right? So this is also led to the so-called tame-while dichotomy in the representation theory. I think the major result there is backward.
The tame is the one which respects the partition as the orbit, and the while it brings now.
Oh, well, not quite.
No?
Tame is something, classifiable in the Jordan normal form sense. Wild is something reduced by the containment relation reduced to classifying pairs of matrices under conjugation action. That's the NP complete problem here. So yeah, that's the tame-while dichotomy. Okay. So using this relation to compare group orbits, we see that matrix equivalence does not contain matrix conjugacy, right? Because their matrix equivalence, you have only n+1 orbits, it's finite. Matrix conjugacy, on the other hand, is infinite at least, right? The over algebra closed field. So there, you don't have such containment relation. But on the other hand, for three-way arrays, all the 5 natural actions, they actually contain each other. That's the distinction between the 2 tensors and 3 tensors. By the 5 natural actions, this is the 3 tensor action, right? This is the P group from what we get from P group. This is the cubic form. This is the algebra iso. And this is, I don't know, matrix space conjugacy or something. I don't know a very clear, reference for this in the literature, but apparently could be useful. So we show that these natural actions, they contain each other. Of course, for example, here we want it to be symmetric, right? We want it symmetric, so also we need the underlying tensor structure to satisfy these symmetric conditions or skew symmetric conditions. Or for such algebra, you need to satisfy, it should be an algebra, right? It should satisfy associativity or different identity. So that's what we do essentially. We show that all these 5 actions, they contain each other.
But containment is enough for a reduction, for polynomial-time reduction.
Yes, you will see. Okay, that's what we are going to do. Okay, so there are 2 techniques. The first one is the Gelfand-Paramanov method, which is putting a given 3-way array to operate a corner of a larger 3-way array. But this one we will not go into, but let's look at the complex theoretic one. We are, come guessing. My background is theoretical computer science, so I like gadgets. And the gadgets actually are something you will find familiar if you work in combinatorics, for example, especially when you look at so-called colored graph isomorphism. That is, you have 2 graphs, the vertices are colored, and you want to find isomorphism preserve the color. Namely, you want to find isomorphism that maps red to red and blue to red, blue vertices. And then the question here is how to encode such color information by some gadgets. So we reduce back to plain graph isomorphism.
Maybe it's interesting that one of the first results in with efficient algorithm in graph isomorphism was Babai probably when he was 12 or something, maybe 20. And he proved that if you have 2 graphs and they are colored and the color classes are bounded, you have many 5, red 5, blue 5, green, blah, blah, blah. This problem, which still seems like exponential, both course will be exponential 30, shows that this is in polynomial-time.
And that's Babai's favorite paper. His favorite.
Is it his favorite?
It introduced the Las Vegas algorithm. It also
publicity.
It also introduced the group theoretic method.
So in there, you're allowed to map one color to another color
Yeah, so you're restricted in your isomorphism. Red has to go to red, right?
Red has to go to red, or red has to go to some other
No,
color?
no, no.
Red
has to
go to
go
red.
red.
You
But
preserve
you know, for each color, you have constant
Okay.
numbers, so that's one. Yeah, he uses good theory, so.
a lot of things go back to the good old days, 1980s. Okay. So, okay, so if you think about it for a couple of minutes, you probably realize how to do it. There are several ways to do it. You want to make the red vertices to be distinct from the blue vertices, right? So the idea there is you want to, for example, enlarge the degree. You introduce some extra vertices, we call it the star gadgets, so that you connect every red vertex to all these star new vertices.
The purpose of this is to remove the colors.
Remove the color, exactly, yes.
You want to connect each color to something unique,
Yes,
a constant sign.
yes. So this is, this is the star gadget. By the star gadget, you are imposing that the red vertices must be mapped to red vertices because their degree is large enough. So for example, if the graph is order n, you had n plus 1 vertices, for example. So this is the star gadget. And what we do for this linear algebra setting is essentially we are doing some star gadget. Of course, then we need to develop further as well.
I just want to connect what we do to the analog of color is the imposition that two matrices have to be the same.
Exactly,
Right.
You will see this. So let's look at this gadget in the linear algebra setting. In the linear algebra setting, suppose we want to reduce the 3 tensor action, UVW, to the group iso action, where you have skew symmetric bilinear maps S cross S to T, such that F and G are isomorphic under GLU, GLV, GLW, if and only if F star G star are isomorphic under GLS, GLT. So we want to do this, right? So we start with such a tensor. First, we want to satisfy this skew symmetric condition. But this is, at the end of the day, it's a lot of child's play. It's like you have blocks, then you permute the blocks somehow. So you start with such a tensor A. You want to make it skew symmetric. You put A in one corner and minus A transpose along this direction in the other corner.
This trick is known in linear algebra since the 1800s.
Yeah, of course, yeah.
But now you see it's 3-dimensional.
3-dimensional.
No, but it's just a 2 by 2. You see, it's only 2-dimensional in the extension.
Exactly. So far, it's as you suggested, it's something we have been doing for 200 years, maybe. But on the other hand, now we want to look at GL on this whole thing, right? So this construction does not quite work in the sense that GLS, which is the direct sum of U and V, may mix U and V somehow. And we want to prevent such mixing. So you can see now the flavor is quite like the graph as color graph iso setting, right? We also want to prevent mixing of vertices. Here we want to prevent mixing between subspaces. So we need something like star gadget. We are making all these, for example, these slices. We attach identity matrices of large enough size, like this, like a stair, Then for this part, in order to avoid mixing, we are making the ranks of these slices to be full, so that you don't really mix, right? So you do that. Of course, because it's skew symmetric, you need to add the slices here too.
Does this picture explain why this doesn't work for matrices? Is you don't have that third dimension?
Exactly. Yes. For 2-dimensional, we don't know, right?
No, you know it's not true.
It's not true, right?
So somehow this 3-dimension gives you room to attach these gadgets that you have.
Exactly. Okay, so this is a gadget. And to prove that the gadget works as intended, it can be a little bit lengthy, which is not very interesting. Sometimes you use a little bit algebra Schmidt, but that's okay. And then if you want to apply to other settings, it will lead to a lot of this type of child's play. For example, consider the reduction from, here is basically saying that you have skew symmetry on the two directions, and the third direction is irrelevant, independent from these two. Now suppose you have skew symmetry on all the three directions. So you want to do some reduction like that. So you start with a tensor with skew symmetry on the two directions. You want to produce a tensor with skew symmetry in all three directions, which I don't know this one, if this one is, I don't know, from the 200 years ago or not, but you can do that with appropriate signing and so on. You put this one here, this one here, this one. So, but now W tilde, this will be U direct sum V, right? So we still need to somehow distinguish between U and V. So we need to attach the gadget. And this gadget can be attached like something like that. So it's in three directions. Somehow, this is like a lot of identity matrices put in the stair shape. Then, of course, now proving this requires a little bit more effort. But what is a little bit trickier is if you go to the ring setting. By the way, this gadget was first proposed in Futerni, Groucho, and Sergeychuk. We usually call it FGS gadget. So it can be applied to GLNR, but with certain twists. For example, what is the appropriate rank notion there? We use something called inner rank. I will explain this very soon. And this R needs to satisfy certain diagonal full property. That is, the diagonal matrices should be full rank, which is not true over Z over 6Z. Because if you have a diagonal matrix over this ring, then you can decompose as the tensor product of this column vector with this row vector. So which means that the inner rank of this diagonal matrix is 1 instead of 2. So we don't, such rings we cannot really handle, but if we satisfy diagonal full property like domain, for example, or the when here is a prime power, it satisfies all these properties. And then you need some non-degeneracy stuff in the field case. Non-degeneracy is saying that, okay, the slices are linearly independent. You can reduce from dependent case to independent case, which will help a lot in your argument. But in the ring case, you cannot assume such non-degeneracy. And then the child play becomes somewhat funny at some point. You need to attach the gadgets a lot of times to prevent all this unwanted mixing, as well as because of you don't have non-degeneracy, you need to somehow preserve all these gadgets as well. So it can become technical at the end, but it's a lot of blocks, different colors. So
you give an example of a finite ring where this diagonal full property holds?
Yeah, over all the domain where you don't have all the domain like Z, right? And all the local principal ideal ring, for example, that is that over prime power, all these rings satisfy this diagonal full property. Okay, so yes, so I have some technical aspects of the gadget, but I assume now you get the idea of how these things are working, right? So there will be like different problems with the gadgets where the gadget here is quadratic size, you want to reduce to linear size, and so you need new gadget. And here you are restricting to diagonal block matrices, but sometimes you want to reduce to monomial matrices or diagonal matrices. And you cannot really reduce to diagonal matrices because here things can mix. There is some difference between linear and combinatorics. Maybe I'll just mention one thing. So the FGS gadget and the star gadget, they are quite similar. You can see the idea there. But there's an important difference, that is, if you are restricting to the direct sum of K subspaces, you want to attach identity matrices, right, to the K parts. But the size of the identity matrices will grow exponentially in K. For example, if you have K equal to 3, Then you have this, you want to basically preserve these two slices, and these two slices. The idea will be, okay, we set this to be identity n plus 1. Here we put identity matrices of size 2n plus 2, but it's not enough to put 3n here. Because if you put 3n, you combine these two slices, you also get a rank of 3n. So that is something you don't really have in the combinatoric setting because you don't have two vertices mixed together or linear combined together. But here you have such a problem. So if you have k components you want to preserve, the identity size, matrix size will grow exponentially in k. So there are new things, and because of this, you need to do various things if you want to restrict to different types of groups and so on. So technical things are there, but I think that's conclude the technical aspect. So far so good, or any question? I try to be a little bit slower. Okay, so now then maybe I'll go back to the algorithm side. Okay. So we've seen this table, right? We've seen this table. And so maybe I'll make a few remarks about this worst case algorithm. So as we were saying, if we want to solve isomorphism between n by n tensors over a finite field of order q, the running time now is q to the n to the 1.5. So I should really say that the first breakthrough was made by Xiaorui Sun. He devised an algorithm in time q to the n to the 1.8, and our result basically just improved various technical aspects of his result. It's a pretty interesting algorithm. It's a wonderful combination of probabilistic methods, maximum versus non-commutative rank of matrix spaces. So I think it would be good to talk about this algorithm, next week when I go to the board. And the classification of simple algebras with evolutions and so on. So it's a pretty wonderful algorithm. I'll go to the board and talk about this algorithm next week. And because of the so-called linear length reduction, I mentioned that if I use the so-called FGS gadget attaching top identity matrices, you get quadratic blow-up. But if you do, there's another gadget, I'll give you linear blow-up of the dimensions. Then we can actually have that. You can go directly from here to here. Otherwise, you need to do some technical twists. You can go from tensor iso directly to group iso and get an algorithm for +2 exponent p group n to the O tilde square root log n. Again, the first breakthrough was done by Xiaorui, who gave the algorithm to n to the log n 5/6. So we improved from 5/6 to 1/2. And this breaks the decades-long barrier of n to the log n. So that's
I do want to mention what you told me in the break about that this weird class of groups is actually.
Yeah, this. So
it seems like if you do this, you are,
we
there's
hope.
a theory that may help you get it for all.
So there are two lines of work. The first line is by Bios, and but this is also used, for example, in computational group theory by Cannon and Holt. So they are, if you want to tackle the whole group ISO, for example, right? So what you do is, at least what they do is, to first identify the solvable radical, the largest normal solvable subgroup. And then if you quotient out the solvable normal subgroup, you call it the semi-simple or fitting free. And there you have different structures. There where the finite simple groups come into the picture. You have permutation of them and so on. So they have a theory. Basically, you hopefully you can solve solvable first and then go to the whole, like the semi-simple part. And then you have the P group part, which is kind of sitting at the very bottom, where so far most algorithms just do brute force. And but the hope is that once this part is done much better, then you can use their existing, this solver radical plus semi-simple quotient and to lead through the series and so on to get the whole group ISO. But that doesn't give us a worst case. That's what people do in practice, for example. So this is one reason why this is thought to be a bottleneck, because usually for groups we still should have a lot of structures. work with, right? Have different characteristics subgroups and so on. But for this class of groups, from the group theoretic viewpoint, it's very, you don't find much thing you can make use of. So the hope is that if you can do something here, then you can live through the whole answer. Yes, so I think I'll probably give an outline of this algorithm next week. I hope you are interested. So I think I have like, I don't know, 10, 15 minutes. I talk a little bit about cryptography. I think this is also exciting. So again, let's go back to the 1990s, where people don't know graph ISO is hard or in the worst case, hard or not. So at that time, there are people thinking that graph ISO may be hard enough to use in cryptography, like Brassard and Cryptier and Brassard and Young. So on the other hand, it seems unlikely, not just because of Babai's algorithm like 7, 8 years ago, but also because of McKay's software called Naughty, which was already developed in the 1980s. But are there useful isomorphism problems in cryptography? Actually, yes, because discrete log is the isomorphism problem. So I'll show you. In general, you have this so-called group action framework. That is, you have a group action, G acting on a set S. Of course, you do some generic assumptions like group operations, actions, sampling from G and S. They are all finite, for example, they're both finite. You assume some general things are efficient. Then here, the orbit problem is asking, given S and T in S, given two set elements, are they in the same group orbit or not? And the search version, which is usually people deal with in cryptography, is that you are given two set elements in the same orbit. You know this already. Can you compute G sending S to T? That's the group action framework. So given this group action framework, let's see how do we cast discrete log as an isomorphism problem. Here it's a little bit awkward because here the set S is actually also a group. It's a cyclic group of order P. You exclude identity because that's it's a unique orbit. So that's why our set S, which is a group. The group G then of course it will be the automorphic group of the cyclic field. It's isomorphic to the product multiplicative group of that P. Now the question will be, given G and H are in S, they are in this cyclic group. You want to know whether there exists A such that, because A is identified as a number, so it's just asking whether G to the A equals H or not. So this is discrete law. You can say that it can be cast as isomorphism, or at least a search version of the isomorphism problem. Graph ISO, of course. Here, S is the set of subsets of size 2 subsets. So a lot of subsets, but you know the idea, right? This is just essentially you fix the vertex set to be from 1 to n. Then you are looking at the set of size 2 subsets, and then you take a subset. So it's a power set of this one.
So labeled graph.
Yeah, it's labeled graph, exactly. Just a lot of work, a lot of sets here. But so this is our set, and then you have this group G, which is permuting the vertices. It's a symmetric group. Now you essentially are asking, given two edge sets, you want to know whether the induced action of this G sending this set of edges to that set of edges. So this is a group theoretic formulation. It's not hard, but this is actually in the 1970s when Lux and Babai doing the group theoretic method of group graph ISO. That's the first step, right? Tensor ISO as well, right? Tensor ISO is a set of all trilinear forms, and the group is a direct product of 3 general linear forms. So you can cast all these things into the group action framework. And of course, now we want to understand.
I don't understand something about the discrete logarithm. Why is it? Are you saying it's a special case of the group action framework?
Yeah, I'm casting it as a, first I cast the discrete log.
Version, you know there's only one orbit.
I
The
know,
question is,
okay. You know it's in the.
Which group element moves one to the other?
Yeah,
That's the split already.
that's the search version.
No, because usually I think of G as a
In
primitive element which covers the bubbles, cover everything.
you're right, certainly. There, here is transitive. So it's transitive. There is just one orbit. You exclude the identity element, so it's transitive. And in cryptography, usually people talk about the search version. So yes, so now comes the, so we have the framework, right? We probably want to do something general before going into the very concrete group actions. So here is a very interesting, important definition by Brossard and Young in 1990. So a group action is one way. If for some set element S, this function f subscript s, which is just sending the group element G to the set element of the action of G acting on S. If this function is a one-way function, then we call this group action to be a one-way group action. You can see that so this S will be public. So essentially, this S determines an orbit, right? And then essentially you are given another set element in this orbit. To invert this one-way function will be to compute this G that transform S to the other set element. So you can say this is essentially just a search version of it. So the one-way group action would correspond to the computational discrete law. So there's another assumption, which basically called pseudo-random group action, which corresponds to decisional decay-Hellman. And this is the definition of pseudo-random group action, which I think is very neat. You have a group acting on the set S. You have two distributions. The first distribution, you have S and T, two set elements. They are both randomly sampled from this set S. Then you have the pseudo-random distribution where you have S randomly sampled, and the T will be a random element from the same orbit as S. Here, essentially, you do this T by first fixing S, then random sample a group element, then compute T as, applying that group element to this S. So you have random distribution, pseudo-random distribution. Of course, pseudo-random means we assume that no polytime algorithm can distinguish these two distributions.
The decisional Diffie-Hellman is a little different, but it doesn't matter.
It is the same. To recover Diffie-Hellman, you do this. So here your set S will be pairs of elements.
Pairs, okay. Right. Yeah.
Yes. Yeah, pairs. Then you have, if you have pairs of elements, you have a group, alt CP as before. They act diagonally by sending G and H to G to the A, G to the H to the A. Then random distribution will be pairs of these things, but each pair will be another pair. So we have 4, right? Then finally, you get something like G1, G1 to the A, G1 to the B, G1 to the C, where A, B, C are all random. But the pseudo-random distribution will be, you first have S, which is a pair. Then T will be S raised to some power. So you have, G1 to the B, G1 to the A, B. So finally you get this. So to distinguish these two distributions is essentially just this. There are a couple of versions, but this is one version.
What is distinguishing?
Distinguishing means that maybe I'll give you something, this 4 tuple from random distribution. But maybe I'll also give you this 4 tuple from the pseudo-random distribution. Then I ask you, which distribution am I sampling from?
There must be something quantitative about this. Right? So you're asking whether there exists a polynomial time.
Yeah, there exists a polynomial, right.
Such that what? So it outputs, it's a test, right? So it outputs either yes or no, pseudo-random.
Yeah.
And then what do you want? That
I want the algorithm can distinguish, namely,
the probability that the test is correct does what?
can tell which distribution I'm sampling.
Bounded away from 1/2, the probability is bounded away from 1/2 as what?
Well,
Say yes or no. If you toss a random coin, you'll have success half. So you want to have success, half goes up to.
1/2.
Yeah, you got it.
You just want the algorithm to output two numbers that are separated in the interval 0, 1. on each case. Right? Doesn't have to have, it may not do one. Yeah.
So yeah, decisional Diffie-Hellman can be cast in here. And of course, I may say that if your group action is transitive, then of course the two distributions are the same. So we usually consider intransitive actions. Okay, so after having the security assumptions on the group actions, then you want to find applications, right? For example, you have bit commitment that's known to Brossard and Young digital signature by combining Gorak and Kelly-Wiggerson, which itself is an identification protocol with Fiat-Shamir. And then recently there's a quantum public key encryption by Han, Morimi, and Yamakawa. So it's a they basically produce some quantum bit, as you know, quantum bit as your public key encryption, assuming this thing. But on the other hand, you have this beautiful theory framework. You need some concrete instantiation at the end. If you want to discrete log, it's one way for classical. You also have decisional Diffie-Hellman, but it's not in the quantum sense, right? Because of short everything. Graph iso group action is not one way even for classical. But on the other hand, there's some very interesting result from the study of hidden subgroup problem, for example. Basically the message there is that the standard technique from short algorithm, if you want to extend from a Billion hidden subgroup to hidden subgroups for symmetric groups, for example, where we care about in the graph iso setting, the standard technique does not work. You need some really new ideas or new quantum routines if you want to solve graph iso, for example, better than classical. And more Russell-Varani, they say that this is the strongest such evidence we have about the limits of quantum evidence so far.
Meaning this paper?
Yeah, this paper, basically. Now, of course, the proposal is that tensor iso seems to be a candidate. It seems difficult in practice, right, as we've seen for the algorithm side. And also it inherits this resistance to standard techniques because here is general linear group, but essentially their work applies to groups that are non-abelian enough in a sense, or you have large irreducible representation dimensions.
Can you explain? So they talk about hidden subgroup.
Yep.
How does that relate to tensor iso?
You relate tensor iso by, it's easier to do graph iso, for example. You reduce to graph auto, right? And then the hidden subgroup is essentially the automorphic group of your graph. And graph iso reduces to graph auto, right? So if you can compute a graph auto, then you can resolve graph iso. There is some similar story. Okay, so I think we are coming to the end. So yes, now we want to say that tensor iso is a candidate for pseudo-random group action. In other words, we need to distinguish between the random distribution, which are two random tensors, n by n over fq, and the pseudo-random distribution. You first sample a random n by n tensor, then you apply random transformations. L, R, T on the three directions, get another B. Then I'm asking you, can you distinguish the two distributions? To distinguish these two distributions, it's useful enough to find some so-called useful invariant. Useful means first it's efficiently computable. Second, it means that it's distinguishing enough. Namely, if you have two random tensors, you should have different values.
Maybe we should say that invariant is something which has a constant value like every object.
Yeah, it has invariant should here an invariant means isomorphic invariant. Should means you have the same value for each orbit. Because here you say that these two things in the random distribution A and B are unlikely to be in the same orbit. But here it must be in the same orbit, right? So as long as you can find some isomorphic invariant, efficiently computable and distinguishing enough, you are good. So this assumption then basically is indicating that currently we don't know such an invariant. For example, tensor rank. Tensor rank is not even efficiently computable. And furthermore, if you have two random tensors, their tensor rank are likely to be maximum. So tensor rank is not satisfying either of these requirements. and we don't know. And furthermore, many of the tensor complete problems are also eligible for this because there are some technical aspects, but in principle, they are also eligible for this.
Is it important that your random distribution is uniform at random? For example, what if you drew sparse tensors, right?
That's a very good question. We don't know. Yeah, we don't find out.
The story could be completely different.
Yeah, that's true. Yeah, we haven't really thought about the structure tensor like sparse and so on. But and also that will be useful because actually in practice, the tensors, for example, in the digital signature by Gorak and Polynomials via Shamir, the tensors will be a public key. So if the tensors are sparse, it will reduce the public key size very long. So and there's one note is that tensor iso over orthogonal groups is not pseudo-random because there the story is that you can flatten the tensor into a very long matrix and then do some inner product of these two matrices, then the singular value will serve as some useful isomorphic invariant. So there, when it comes to all the practical values, of course, then all practical things, a lot of different changes may matter. So I just want to warn you that tensor iso over orthogonal, not pseudo. So we are done, kind of in time. So just to recall, so we have tensor iso as a complexity class. We start with GLNF, invertible matrices, go to class, where class means group class, or we change from F to R, where R is a commutative ring. Then we look at the technical aspects. We kind of get an idea, right, of the Fraternity-Groucho gadget. It's a linear algebraic analog of the star gadget. And we didn't really touch these things, but they are like technically get the idea. Finally, we talk about their algorithm and the cryptography aspects, especially it's a candidate for the pseudo-random group action.
Candidate, anybody implements it?
I did, yeah.
No, I mean component or anybody.
Not yet.
Post-quantum cryptography.
There are proposals.
Okay. Nobody still.
Yeah, it's more in the experiment.
They all use the lattice.
So far, lattices, yeah. So I think finally, it's probably, I still have a few minutes. I'll just mention some I think they are pretty easy to state problems. There are a lot, you can imagine this kind of like an emerging theory or something. There are a lot of open problems here. So first, remember that the symmetric for those, representation theory, symmetric trilinear forms and alternating trilinear forms, they are irreducible representations of GLNF, where the symmetric product of symmetric cube will be corresponding to irreducible representation of this one row, the Young diagram one row. Alternating will be the Young diagram one column. And there's, of course, a third one. What about the orbit problem for this action? You do the representation corresponding to this one, Young diagram to this one. This tensor is more than complete. Because these two are tensor is more than complete, we don't really know about what will happen for this. It will be strange if it's not tensor is more complete. Tensor iso over GLNQ, is this decidable or not? We don't know. Decidability is even a problem. And is tensor isomorphism orthogonal equal to tensor isomorphism GL? I used to think that is probably not the case, but recently Lisikov and Water, they show that this is true if you are not about orbit problem, but about orbit closure intersection, then it's true. If you look at, instead of tensor iso, you look at the tensor orbit closure intersection over orthogonal over GL, then it's true. So it makes me wonder this may be true for iso as well. And of course, are there better complexity bound for tensor iso over GL3, just to go from 2 to 3? Is tensor iso group action pseudo-random, right? There's a possible approach via hyperdeterminant like Jukes and Yanen. So if hyperdeterminant, I think the idea is that they don't know how to show that this is VMT complete. So there's a small chance that this may serve as a useful invariant. And finally, tensor iso reductions over GLN Z over 6Z, because there we don't have this, we have this funny thing, this it's not a diagonal form, so we don't know how to do a lot of things. Okay, thanks a lot.
Comments or questions?
So I hope I'm not going too
Plenty.
fast.
I think that's all.
Okay.
Okay, so until next week.